Guys, the purpose of this video is to tell you that a graph is not the only way that you can solve an internal standard problem. And you're going to see that in this example. So yes, most of the time we are plugging in standards and standard sets and making calibration curves and then applying the samples to the calibration curve itself. But in this example, you're going to see that an entire curve is not required. The only thing we need is the response factor, or the ratio. And if we can determine what the ratio is, then we can kind of assign that to all of the other samples that's included in the set as well. So here in this practice problem, it says in a chromatographic equipment, or chromatographic equipment, a solution containing 0.0837 molarity X and a 0.066 molarity S give peak areas of A sub X is 423 and A sub S is 347. To analyze an unknown, 10 mils of a 0.146 S was added to a 10 mils of X, and the mixture was diluted to 25 mils. The mixture gave a chromatography spectrum with area of A sub X 553 and A sub S of 582. Find C of X. All right, there's a couple of things I want to bring to your attention here. This came from a university PowerPoint slide. The university is in Michigan, and there's no such thing as chromatography spectrum. That is a very strange, weird word that probably a TA put into place, or that a TA that probably cannot speak hardly any English decided to write down. The chromatography spectrum, what they're referring to is the chromatogram. That is the proper term that needs to be used there. Chromographic equipment's kind of a weird word, but it is out there. It's just not used that often. Okay, so how can we solve for the unknown based on this data? Based on these numbers, based on these values, what on earth can I do to solve this problem? And the very first thing that you're going to have to do is look at your standard. The standard is from the bullet up at the top. Contains 0.0837X and 0.066S, and it gives you the areas for each one of those. So we need to use that relationship, and we need to figure out a ratio with that relationship first before we do anything else. So I'm going to write down a few numbers from the previous slide. And we said that that standard that I have made, I know what's in that standard. I've analyzed that standard. We know the concentrations. 0.0837 molarity of X and 0.0666 molarity of S gave me a signal of 423 and 347. I need to do something with these values. How do I do this algebraically without a calibration curve? Well, here's the equation that they like for you to use. A sub X over C is equal to F times A sub S over C. All right, so this X and the S are pretty important. The S and the X represent, and of course these are X's and S's as well, they represent either the standard or the internal standard that you are using. All right, so the solution containing 0.0837X, that is typically representative of the standard. So A sub X is 423, that's the absorbance. And what was the concentration based on that absorbance? 0.0837 equals F times, I know the ratio. The S typically is the internal standard, so 347, that's the signal, over the concentration of that, which is 0.0666. Okay, so I'm going to bring up the calculator, And we're just going to kind of clear up the things that are on each side of that equal sign. So 423 divided by 0.0837 equals 11,432. And if I clear up this 347 divided by 0.0666, that gives me 5210. And to solve for f, I'm going to divide each side by 5210. So 11,432 divided by 5210. That's equal to 2.1942. And I think there could be a mistake. Let's check this first number again. 423 divided by 0.0837. That just doesn't look right. So I'm going to hit equal. Yeah, that's what I thought. That's a much better number. 5053 or 5054. So we need to go in and do this calculation again. 5054, not 11,000 and some. All right. So 5054. And then I'm going to take that number and I'm going to divide it by 5210, and that gives me 0.970. All right, so that's an F factor. There we go. Okay, the F factor can be greater than 1. It can be less than 1. It doesn't really matter. You know, I just kind of looked at the numbers after I did it and realized that 11,000 looked a little bit bigger, and that's why I double checked it. So 0.970 is what we would call the F. So that's the F factor, and this is going to be the number one step every single time you solve these algebraically. Determine the F factor, and this is based on the standards, right? So here are the standards. My internal standard is inside of there. I know the concentrations. I know the signals from the machine. I know how they're related to each other. And then this is the equation over here to the right-hand side that we used in order to determine that F factor. Quite honestly, as long as you keep these things consistent, you're going to be okay. So if you switch these numbers around and put maybe your X values over here and your S values over here, you're going to get a different F. But if you carry that through the same way all the way through, then you're going to be okay. You'll get the same answer in the very end. So don't worry about which side is the proper side. You just need to be consistent all the way through, and you'll eventually get the correct answer. So the second part here is that it gave us a curveball. And it said to analyze the unknown 10 mils of a 0.146 molarity S and 10 mils of a X was diluted to 25 milliliters. And they wanted to know what on earth is the concentration of the unknown, right? That's what they're after. So we've got to use this F factor in order to help us determine what the concentration truly is. That's that relationship. The problem is that there is a dilution that's involved here. It looks like we've took 10 mils of this stuff and 10 mils of that stuff, and we've added it all together. Notice that this was an internal standard, right? I told you this was typically S stands for the internal standard. The same thing's happening here. We took 10 mils of a 0.146 molarity of the internal standard, and that's why that was listed as a S down below. So this was a known concentration and a known amount, and this was an unknown concentration of X. That's what we're trying to solve for. So that's why I did the setup the way that I did it. Okay, so we need to figure out what the actual concentration of the internal standard was. It's not just 0.146, right? We took 10 mils of that and we diluted it to 25. So we've got to figure out what the actual concentration for the internal standard is before we do anything else. So CV equals CV. I know that the initial concentration was 0.146, and I took 10 mils of that stuff, and I want to know what that concentration is of the internal standard after I diluted it to 25 in total. That's what the problem told me to do, and that's how it said that that sample was prepared. So it's just a simple dilution problem. That's all that it is. All right, so I'm going to pull up the calculator. So I'm going to take 0.146, I'm going to multiply that by 10, that gives me 1.46, and then I'm going to divide by 25 to solve for x, and 0.0584 is the concentration, 0.0584 molarity. And that is the molarity of the internal standard. So if I go back to this equation up here that I've circled in purple on your screen, I'm going to see some different pieces of the puzzle that's going to start to fill in. I now know the F value. I now know the concentration of the internal standard. So C sub S now is what I know. It also told me the signals. I've not written those down yet, but it told me the signals of those in the problem. So I'll know A sub S and A sub X, and I will be able to calculate for the concentration of X. So I'm going to write this up here at the very top, 0.0584 molarity of my internal standard. And what I'm going to do is I'm going to pause the video for a few minutes. I'm going to erase everything on the screen except for that equation that you're seeing over to the right or to the left. And I'm going to write down the F value as well because we'll need it too. So 0.970. So I'm going to pause it here. I'm going to erase all of this, and we're going to pick up in just a blip of a second. All right, so I've erased all the junk that was on the screen up there before that we've already solved. And I wrote in the areas down here at the very bottom for you. So in the problem, it said that the A sub X, the signal, for the unknown that we're trying to solve for is 553, and the area for the internal standard was 582. So we need to use those numbers eventually in this equation, but those numbers came from the problem that we showed you just a couple of minutes ago. All right, so here I told you that we have the molarity of the internal standard now because that got diluted. We have the ratio, what we would call the F factor, and the problem wants us to solve for the concentration of the unknown. So I've got to use the same equation, the same thing all over again, right? Keep it consistent. The way that you've written it in the beginning is the way that it should be solved for now. So X's were over to the left and S's were over to the right. So the A sub X, that is the signal from the sample. So the signal from the sample was 553 divided by C sub X. That is the concentration of the unknown, and that's what I'm trying to solve for. So that's going to stay as the variable. The F is the F factor. That was that ratio that we just solved for based on the data from our standards that I made. Okay, that F was described a few minutes ago to be 0.970, and then we're going to multiply that by another fraction. The A is the signal of the internal standard, so 582, it came from the problem, and C sub S, that's the concentration of the internal standard. We had to use the dilution equation to solve for that, right? Because it was 10 mils diluted to 25. So up here, this concentration is 0.0584. So I need to solve this equation for the variable, and I'm going to bring in my calculator to help me do this. So 553 divided by C sub X equals, I'm going to start with the fraction first, 582 divided by 0.0584. That gives me 9,965, and then I'm going to multiply that by 0.970, right? So that gives me 9,666.7. 9,666.7. 666.7. To solve for this variable, I would multiply each side by c sub x. So I would get 553 is equal to 9,666.7 c sub x. And then to solve for c sub x, I would divide each side of the equation by 9,666.7. So c sub x is equal to 553 divided by 9,666.7. And that gives me an answer of 0.0572. Okay, so that's great and all. The problem, though, is that this got diluted, just like my internal standard did. If it didn't get diluted, that would be my concentration. I would report that number, and there it is. The problem is that 10 milliliters of that sample was diluted to 25. So there is a dilution that's embedded here. So my final step is to do a back dilution to get to the true answer of the original before it got diluted. So I want to know, what is the concentration of the original? I took 10 milliliters of that and I diluted it. Well, when I diluted it, my concentration is 0.0572, and I ended up making a total of 25 milliliters. So this is a CV equals CV, another dilution problem. That's all that it is. That's the original concentration. I took 10 mils of it. I now know what the final concentration is that was analyzed and ran, and I know the volume of that. It told me it brought it to 25 mils in total. So I'm going to bring the calculator up again. This time I'm going to go in and take 0.0572. I'm going to multiply by 25, and then I'm going to divide by 10, and my answer here is 0.143. So 0.143 molarity is the concentration of the component that's in that sample. And we did this without using a calibration curve. I based it off of one ratio, and that is it, right? Now, if I had a choice between the two, the calibration curve is going to be much better. The reason is because it takes ratios of more than one, and it puts them on a graph, and it takes into account 4 or 5 different standards. With this typical setup, it's only bringing into the picture one ratio for one standard, and I'm basing all the calculations off of that one. Well, what if there was something wrong with this particular standard? Then there's going to be something wrong with this particular setup and the final answer in the end, which is why the calibration curve is typically the one that's always used, but we don't have to have it. This is a way that we can do it algebraically, a very quick check to figure out what we have, to get us into the ballpark figure of what to expect when we analyze and when we report this sample from this point on. So 0.143 is going to be the answer, and you only need that one equation up there at the very top in order to solve these types of problems. Yeah, dilution's in the play. Dilution's always in play. I'm not really counting that equation. All of that kind of stuff, this is things that you should know how to do. The equation that's the most important is the one up there circled in purple. So make sure you write that down. Make sure that you feel comfortable with what those variables stand for, and I think that you'll be able to solve these types of problems without any issues.